When UPS systems shut down during generator tests, several potential causes need investigation. Firstly, check for generator frequency and voltage issues. Ensure the generator provides stable frequency and voltage within the specified range for the UPS. Fluctuations or deviations can interfere with UPS operation. Secondly, verify UPS settings misconfiguration. Verify that the UPS settings such as voltage thresholds, battery backup time, and load shedding parameters are correctly configured. Improper settings can trigger premature shutdown. Thirdly, inspect the UPS generator interface. Ensure that the UPS is properly interfaced with the generator. Check connections, signal wires, and communication protocols. Fourthly, assess UPS battery health. Batteries that are old, damaged, or not properly charged can compromise UPS performance. Conduct battery tests to assess their condition. Fifthly, examine generator synchronization issues. If multiple generators are being used, verify that they are synchronized properly during the test. Unsynchronized generators can cause power fluctuations that disrupt UPS operation. Sixthly, analyze electrical noise. High levels of electrical noise from the generator or other equipment can interfere with UPS electronics. Check for sources of noise and implement mitigation measures. Seventhly, check for load imbalance. Ensure that the load being supplied by the UPS is balanced across all phases. An even load distribution can overload certain phases, leading to UPS shutdown. Eighthly, investigate generator fuel issues. Insufficient fuel supply or poor fuel quality can affect generator performance and stability. Check fuel levels and consider testing the fuel. To effectively troubleshoot, follow these steps. Firstly, gather data. Obtain event logs, UPS settings, and any relevant documentation. Secondly, inspect equipment. Visually examine the generator, ops, and wiring connections for any obvious issues. Thirdly, test the generator. Conduct tests to verify generator frequency, voltage, and synchronization. Fourthly, test the UPS. Perform diagnostic tests on the UPS, including battery tests, load tests, and voltage checks. Fifthly, review settings. Check UPS and generator settings to ensure they are appropriate for the specific conditions. Sixthly, analyze event logs. Review UPS event logs to identify any error messages or patterns that may indicate the cause of the problem. Seventhly, inspect electrical noise. Use a spectrum analyzer to detect and locate any sources of electrical noise. Eighthly, monitor load. Monitor the load supplied by the UPS to ensure it is balanced and within the specified limits. As additional tips, consult with the generator and UPS manufacturers for technical support and specific troubleshooting guidance. Document all troubleshooting steps and findings thoroughly. Consider using a power quality analyzer to monitor voltage, frequency, and electrical noise during generator testing. Consider checking the static transfer switch operation. A static transfer switch, or STS, is a device used to automatically transfer power between two sources. It's often found in systems with uninterruptible power supplies, or UPS, to provide a seamless switchover to a backup power source in case the primary source fails. An STS uses solid-state devices like silicon-controlled rectifiers, or SCRs, to quickly switch between power sources, typically in a matter of milliseconds. This ensures that critical loads, such as computer systems or medical equipment, continue to receive uninterrupted power. The key components of an STS include the solid-state switching devices, control logic, and monitoring systems. The control logic continuously monitors the quality of both power sources. If the primary source falls outside of acceptable parameters, such as a voltage drop or complete loss of power, the control logic initiates a transfer to the backup source. The solid-state switches then rapidly connect the load to the backup source, minimizing any disruption to the equipment being powered. There are two main types of STS: open transition and closed transition. An open transition STS briefly interrupts power during the transfer. While the interruption is very short, typically a few milliseconds, it can still be problematic for sensitive equipment. A closed transition SDS, also known as a bumpless transfer switch, avoids any interruption of power. It does this by momentarily paralleling both power sources before disconnecting the primary source. This ensures a seamless transfer without any disruption to the load. An STS is commonly used in data centers, hospitals, and other facilities where a continuous power supply is critical. It provides a reliable way to switch between power sources, ensuring that critical equipment remains operational during power outages or other power disturbances. One of the main advantages of an SDS is its speed. The solid-state switches can transfer power much faster than mechanical switches, reducing the risk of equipment damage or data loss. Another advantage is its reliability. Solid-state devices have no moving parts, making them less prone to failure than mechanical switches. When selecting an STS, it's important to consider the specific requirements of the application. This includes the voltage and current ratings, the type of load being powered, and the desired transfer time. It's also important to choose an SDS from a reputable manufacturer to ensure its quality and reliability. Proper maintenance is essential for ensuring the continued reliable operation of an STS. This includes regular inspections, testing of the switching function, and replacement of any worn components. Some common problems that can occur with an SDS include failure of the solid-state switches, malfunctioning control logic, and overheating. Regular maintenance can help prevent these problems and ensure that the SDS is always ready to switch to the backup power source when needed. When troubleshooting issues with an SDS, it's important to follow a systematic approach. Start by checking the power sources to ensure that they are both within acceptable parameters. Then check the control logic to ensure that it is functioning properly. Finally, check the solid-state switches to ensure that they are switching correctly. If you're not comfortable working with electrical equipment, it's best to consult a qualified electrician. Working with electricity can be dangerous, and it's important to take precautions to avoid injury. Some advanced features that may be found on an SDS include remote monitoring and control, data logging, and automatic testing. These features can help improve the reliability and efficiency of the power system. In summary, an SDS is a critical component of any system that requires a continuous power supply. It provides a reliable way to switch between power sources, ensuring that critical equipment remains operational during power outages or other power disturbances. By understanding how an SDS works and following proper maintenance procedures, you can ensure that it will provide years of reliable service. Consider checking the grounding of the equipment. Proper grounding and bonding are critical for the safe and reliable operation of electrical systems. Grounding refers to the connection of electrical equipment and circuits to the earth, while bonding involves connecting metallic parts to create a low impedance path for fault currents. The primary purpose of grounding is to protect people from electric shock. In the event of a fault, such as a wire coming into contact with a metal enclosure, the ground provides a low resistance path for the fault current to flow back to the source. This high current causes the overcurrent protection device, such as a circuit breaker or fuse, to trip, quickly disconnecting the power and preventing a dangerous voltage from being present in the equipment. Bonding serves a similar purpose by ensuring that all metallic parts of an electrical system are at the same potential. This reduces the risk of electric shock if someone comes into contact with two different metal parts that are at different voltages. The National Electrical Code, or NEC, provides detailed requirements for grounding and bonding. These requirements are designed to ensure that electrical systems are installed and maintained in a safe manner. Some of the key NEC articles related to grounding and bonding include Article 250, which covers grounding and bonding in general, and Article 680, which covers grounding and bonding of swimming pools and similar installations. There are several different types of grounding systems, including the grounded system, the ungrounded system, and the impedance grounded system. In a grounded system, one of the conductors is intentionally connected to ground. This is the most common type of grounding system used in residential and commercial buildings. In an ungrounded system, none of the conductors are intentionally connected to ground. This type of system is typically used in industrial applications where a high degree of reliability is required. In an impedance-grounded system, an impedance such as a resistor is connected between one of the conductors and ground. This limits the amount of fault current that can flow to ground, reducing the risk of damage to equipment. Bonding is typically accomplished by connecting all metallic parts of an electrical system together with a conductor. This conductor is then connected to the grounding electrode system, which consists of one or more grounding electrodes that are buried in the earth. Common types of grounding electrodes include ground rods, ground plates, and metal water pipes. When installing grounding and bonding systems, it's important to follow the NEC requirements carefully. This includes using the correct size conductors, making sure that all connections are tight and secure, and properly identifying all grounding and bonding conductors. Regular inspection and testing of grounding and bonding systems is also important to ensure that they are functioning properly. This includes checking the resistance of the grounding electrode system and testing the continuity of bonding connections. Common problems that can occur with grounding and bonding systems include corroded connections, loose connections, and damaged conductors. These problems can reduce the effectiveness of the grounding and bonding system and increase the risk of electric shock. When troubleshooting grounding and bonding problems, it's important to use the correct test equipment and follow proper safety procedures. This includes using a low resistance ohmmeter to check the resistance of grounding connections and using a voltage tester to check for voltage on metallic parts. If you're not comfortable working with electrical equipment, it's best to consult a qualified electrician. Working with electricity can be dangerous, and it's important to take precautions to avoid injury. Some advanced grounding and bonding techniques include the use of equipotential planes and isolated ground systems. Equipotential planes are used to create a low impedance path for fault currents in areas where there is a high concentration of electrical equipment. Isolated ground systems are used to reduce electrical noise in sensitive electronic equipment. In summary, proper grounding and bonding are essential for the safe and reliable operation of electrical systems. By following the NEC requirements and performing regular maintenance, you can ensure that your electrical system is properly grounded and bonded. It would be good to verify the transfer switch operation. Transfer switches are essential components in electrical systems, providing a means to switch between different power sources. They are commonly used in emergency power systems, where they allow a building to switch from the utility power grid to a backup generator during a power outage. There are two main types of transfer switches: automatic transfer switches or ATS, and manual transfer switches. An automatic transfer switch automatically switches between power sources when it detects a power outage or other power quality problem. A manual transfer switch requires a person to manually switch between power sources. Automatic transfer switches are typically used in critical applications where a continuous power supply is essential, such as hospitals, data centers, and emergency services facilities. Manual transfer switches are often used in residential and small commercial applications where a brief interruption of power is acceptable. The key components of a transfer switch include the switching mechanism, the control logic, and the monitoring system. The switching mechanism is responsible for physically connecting the load to the selected power source. The control logic monitors the voltage and frequency of the power sources and initiates a transfer when necessary. The monitoring system provides information about the status of the transfer switch and the power sources. When selecting a transfer switch, it's important to consider the specific requirements of the application. This includes the voltage and current ratings, the type of load being powered, and the desired transfer time. It's also important to choose a transfer switch from a reputable manufacturer to ensure its quality and reliability. Proper installation is essential for ensuring the reliable operation of a transfer switch. This includes following the manufacturer's instructions, using the correct size conductors, and making sure that all connections are tight and secure. Regular maintenance is also important to ensure that the transfer switch is always ready to switch to the backup power source when needed. This includes regular inspections, testing of the switching function, and replacement of any worn components. Some common problems that can occur with transfer switches include contact wear, coil failure, and control logic problems. Regular maintenance can help prevent these problems and ensure that the transfer switch is always ready to switch to the backup power source when needed. When troubleshooting issues with the transfer switch, it's important to follow a systematic approach. Start by checking the power sources to ensure that they're both within acceptable parameters. Then check the control logic to ensure that it is functioning properly. Finally, check the switching mechanism to ensure that it is switching correctly. If you are not comfortable working with electrical equipment, it's best to consult a qualified electrician. Working with electricity can be dangerous, and it's important to take precautions to avoid injury. Some advanced features that may be found on transfer switches include remote monitoring and control, data logging, and automatic testing. These features can help improve the reliability and efficiency of the emergency power system. In summary, transfer switches are essential components in emergency power systems. They provide a reliable way to switch between power sources, ensuring that critical loads remain operational during power outages or other power disturbances. By understanding how transfer switches work and following proper maintenance procedures, you can ensure that they will provide years of reliable service. Consider checking the harmonic distortion levels. Harmonic distortion is a type of power quality disturbance that can cause problems in electrical systems. Harmonics are sinusoidal voltages or currents that are integer multiples of the fundamental frequency, which is typically 60 Hz in the United States. For example, the second harmonic is 120 Hz, the third harmonic is 180 Hz, and so on. Harmonic distortion is caused by nonlinear loads, which are devices that draw current in a non-sinusoidal manner. Common examples of nonlinear loads include electronic devices such as computers, televisions, and fluorescent lighting, as well as industrial equipment such as variable frequency drives and arc furnaces. When nonlinear loads draw current, they create harmonics that propagate throughout the electrical system. These harmonics can cause a variety of problems, including overheating of equipment, increased energy losses, and malfunction of sensitive electronic devices. The level of harmonic distortion in an electrical system is typically measured using a total harmonic distortion, or THD meter. THD is expressed as a percentage of the fundamental frequency and represents the ratio of the root mean square, or RMS, value of the harmonic content to the RMS value of the fundamental frequency. High levels of THD can indicate a serious power quality problem. There are several standards that limit the amount of harmonic distortion that is allowed in electrical systems. These standards include IEEE Standard 519, which provides recommended practices and requirements for harmonic control in electrical power systems, and IEC Standard 61032, which sets limits for harmonic current emissions from equipment connected to low-voltage systems. To mitigate harmonic distortion, several techniques can be used. These include using harmonic filters, which are devices that block or reduce the amplitude of harmonic currents, using harmonic mitigating transformers, which are transformers designed to reduce the generation of harmonics, and using power factor correction equipment, which can help to reduce the amount of harmonic current drawn by nonlinear loads. When troubleshooting harmonic distortion problems, it's important to use the correct test equipment and follow proper safety procedures. This includes using a harmonic analyzer to measure the levels of individual harmonics and using a current clamp to measure the current drawn by nonlinear loads. It's also important to understand the characteristics of different types of nonlinear loads and how they contribute to harmonic distortion. If you're not comfortable working with electrical equipment, it's best to consult a qualified electrician or power quality engineer. Working with electricity can be dangerous, and it's important to take precautions to avoid injury. Some advanced harmonic mitigation techniques include the use of active harmonic filters, which are electronic devices that inject harmonic currents into the electrical system to cancel out the harmonic currents produced by nonlinear loads, and the use of hybrid harmonic filters, which combine passive and active filtering techniques to achieve optimal harmonic mitigation. In summary, harmonic distortion is a power quality problem that can cause a variety of problems in electrical systems. By understanding the causes and effects of harmonic distortion and implementing appropriate mitigation techniques, you can ensure that your electrical system operates reliably and efficiently. Make sure you check the power quality. Power quality refers to the characteristics of the electrical power supply. A good power quality supply is one that provides a stable voltage and frequency with minimal distortion and interruptions. Poor power quality can cause a variety of problems in electrical equipment, including malfunction, damage, and reduced lifespan. There are several different types of power quality disturbances, including voltage sags, voltage swells, voltage transients, harmonic distortion, and frequency variations. Voltage sags are momentary reductions in voltage, typically lasting from a few milliseconds to a few seconds. Voltage swells are momentary increases in voltage, also typically lasting from a few milliseconds to a few seconds. Voltage transients are short-duration, high-amplitude voltage spikes. Harmonic distortion is the presence of harmonic frequencies in the voltage or current waveform. Frequency variations are deviations from the nominal frequency, which is typically 60 Hz in the United States. Power quality problems can be caused by a variety of factors, including faults in the power grid, switching of large loads, and operation of nonlinear loads. Nonlinear loads are devices that draw current in a non-sinusoidal manner, such as electronic devices and variable frequency drives. To assess power quality, several different types of test equipment can be used. These include voltage recorders, current recorders, harmonic analyzers, and power quality analyzers. Voltage recorders measure the voltage over time and can detect voltage sags, voltage swells, and voltage transients. Current recorders measure the current over time and can detect current imbalances and harmonic currents. Harmonic analyzers measure the levels of individual harmonics in the voltage or current waveform. Power quality analyzers combine the functions of voltage recorders, current recorders, and harmonic analyzers into a single instrument. To mitigate power quality problems, several different techniques can be used. These include using surge suppressors to protect against voltage transients, using voltage regulators to stabilize the voltage, using harmonic filters to reduce harmonic distortion, and using uninterruptible power supplies, or UPS, to provide backup power during power outages. When troubleshooting power quality problems, it's important to follow a systematic approach. Start by identifying the symptoms of the problem, such as equipment malfunction or damage. Then use test equipment to measure the voltage, current, and harmonic distortion levels. Finally, analyze the data to determine the cause of the problem and implement appropriate mitigation techniques. If you're not comfortable working with electrical equipment, it's best to consult a qualified electrician or power quality engineer. Working with electricity can be dangerous, and it's important to take precautions to avoid injury. Some advanced power quality mitigation techniques include the use of active voltage conditioners, which are electronic devices that inject voltage into the power system to correct voltage sags and voltage swells, and the use of dynamic voltage restorers, which are similar to active voltage conditioners but can also correct voltage transients. In summary, power quality is an important aspect of electrical system performance. By understanding the different types of power quality disturbances and implementing appropriate mitigation techniques, you can ensure that your electrical equipment operates reliably and efficiently. Remember to check the UPS configuration. Proper configuration is essential for ensuring its reliable operation. The configuration settings determine how the UPS will respond to different power conditions, such as voltage sags, voltage swells, and power outages. Some of the key configuration settings for a UPS include the voltage range, the frequency range, the transfer time, and the battery settings. The voltage range specifies the acceptable voltage levels for the input power. If the input voltage falls outside of this range, the UPS will switch to battery power. The frequency range specifies the acceptable frequency levels for the input power. If the input frequency falls outside of this range, the UPS will switch to battery power. The transfer time is the time it takes for the UPS to switch from utility power to battery power. A shorter transfer time is generally better, as it minimizes the interruption to the load. The battery settings determine how the UPS will charge and discharge the batteries. Proper battery settings are essential for maximizing battery life. When configuring a UPS, it's important to consult the manufacturer's documentation and follow the recommendations. It's also important to consider the specific requirements of the load being protected. For example, sensitive electronic equipment may require a UPS with a very short transfer time and a stable output voltage. To configure a UPS, you will typically need to connect to it using a computer and special software. The software will allow you to view and modify the configuration settings. It's important to make a backup of the existing configuration settings before making any changes. This will allow you to restore the original settings if something goes wrong. After making changes to the configuration settings, it's important to test the UPS to ensure that it is functioning properly. This can be done by simulating a power outage and observing how the UPS responds. Regular maintenance is also important to ensure that the UPS continues to operate reliably. This includes checking the battery voltage, cleaning the UPS, and replacing the batteries when they reach the end of their service life. Some common problems that can occur with UPS configuration include incorrect voltage settings, incorrect frequency settings, and improper battery settings. These problems can cause the UPS to malfunction or to fail to provide backup power when needed. When troubleshooting UPS configuration problems, it's important to consult the manufacturer's documentation and use the correct test equipment. If you're not comfortable working with electrical equipment, it's best to consult a qualified electrician or UPS technician. Working with electricity can be dangerous, and it's important to take precautions to avoid injury. Some advanced UPS configuration features include remote monitoring and control, data logging, and automatic testing. These features can help improve the reliability and efficiency of the UPS. In summary, proper UPS configuration is essential for ensuring its reliable operation. By consulting the manufacturer's documentation, considering the specific requirements of the load, and performing regular maintenance, you can ensure that your UPS will provide backup power when needed.